Hello. In this exercise, I will discuss a 2D earth dam with groundwater flow. First thing I want to do is create a new model. I'll call it 2D earth dam. I will be using the groundwater module in 2D space, steady state calculation. In this case, we'll be using imperial units with a time duration in seconds. The label will be 2D earth dam with flow. I'll hit OK. From there, we should see the window and the 2D Cartesian space popping up. From there, we need to generate the correct boundaries for the model. To do that, we will need to go to View, World Coordinate System. I'll input a manual boundaries for my X and Y axis here. The minimum will be 10, and the minimum vertical dimension elevation will be 400 feet. The maximum horizontal distance will be 700 feet, and it will go to 720 elevation. You can see here that now my axis reflects my coordinate system and that I'm using imperial units. So y and x are in feet, and the Cartesian grid corresponds to the boundaries I've just input into the coordinate system. Great. So now I need to draw my regions. In this example, we'll be drawing our regions in real time. We won't import any geometries generated through an external program. To do that, I will go to my regions window. Here, we can define names for each of the regions we've generated. So my first one I'll call dam. I'll hit new. Hit OK. Make sure that the region I'm working on is dam. And then I need to input the coordinates. So to do that, I will be drawing a polygon. The first coordinate for the polygon is located at x dimension 165. So that's my first point. It extends up to 325 elevation. I'm sorry, 710 elevation, 325 horizontally, and 365, and then down to 525. And you can see here I've generated my polygon now. Now I need to draw the other polygons that make up the 2D geometry. This is essentially a 2D cross-section that we're going to solve a steady state flow calculation. So now, because I'm drawing the second region, I need to make sure that the region option is selected for R2. It means we're drawing the second polygon. Okay, so now I'm going to select the option to draw region polygon. It's going to start at the origin, so 610, and it's going to extend outward to the corner points of the levee, then all the way to the end to 690. And then we're going to go down to this. I'm going to hit finish drawing, and you can see after I've generated the corner points, it automatically generates the polygon. I want to inspect the region now to make sure that everything's inputted correctly. Indeed, here I will need to edit this to make it 505. To make any edits to polygons you've generated, all you need to do is select region properties and manually update the coordinates in this window. You can simply just type them. So in real time, I've updated the coordinates. Hit OK. And you can see here the second polygon region has been generated. I will need to repeat this process 2 more times for the remaining 2 polygons. So I will go to the window, click Create New, hit OK. Then I will need to draw a region polygon. And then this will go down to a deeper depth. So I've now created the third polygon. Notice how it is adjacent to the second polygon. That's not a problem. And then I will need to inspect the region properties and then make sure that everything is correct. Here, this actually needs to be 455 instead of 450. It's easy to edit that. All I need to do is just manually type the new value in the cell. I'm going to hit OK. And now that change is reflected in the GUI. For my final polygon, I need to define a rectangle inside the underneath the core region of the dam. So I will create one more region. I'm going to create new and make sure that the new region is generated. So we're working with the new one we've just created. I'm going to draw the polygon. You can zoom in with the mouse wheel if you want more sensitivity. And that's going to extend down to the deeper layer here. You can see here that there is a lot of sensitivity when it comes to the input, but I can easily correct that by highlighting the polygon, going to region properties, and manually editing these so they don't have any significant figures in the decimal place. And see, now the polygon looks nice and straight. Great. So now we've drawn our 2D geometry. We have a cross section. The next step is to actually define the materials. To do that, I will go to the toolbar, go to the materials manager, then create new. I will call this a silt loom. It will be unsaturated. Then I need to define the volumetric water content. This value is 0.368 with a specific gravity of 2.65. I need to define the water suction curve. To do that, I will choose the fitting method and the data entry. Now I need to go to laboratory data and define my suction curve. Then I'm going to apply the fit. And then I can check the suction curve in the graph data and see that it's actually giving me the correct suction per water content output. Indeed, the curve looks good, so I'm going to hit the X. then hit OK. Now I need to find the hydraulic conductivity. In this case, it's 3.51 times 10 to the minus 4. I can use scientific notation in the LE program. And the hydraulic conductivity will be a constant value. I also need to define the permeability method. And I will use a preset for a silt loom with a minimum conductivity of 1 times 10 to the minus 10 feet per second. Then I'll hit OK. I will generate the second soil material now. As before, I need to define the volumetric water content and the suction curve as a function of volumetric water content. In this case, the saturated volumetric water content is 0.33. And I will be manually putting in data points for my suction curve. And I will continue doing that until the entire curve has been generated. Great. And then I need to double check my graph to make sure that it's producing the correct water retention curve for my given volumetric water content. Indeed, the suction curve looks correct, so I will hit the X, then hit OK. As before, I need to define the hydraulic conductivity. And in this case, it's 1.61 times 10 to the minus 4 feet per second with a modified Campbell permeability calculation. Okay, good. Now I need to generate the third soil, and that is the concrete. We would expect concrete to have a fairly low volumetric water content. And as before, I will be manually generating the suction curve as a function of volumetric water content. It's quite efficient to just use the tab button to manually cycle through the different cells when you're entering data. So I'm just hitting tab and it's cycling to the next cell in the column. Okay, great. Now I need to select apply fit, inspect the suction curve, and indeed it looks correct. So I'm going to hit OK. Then go to the conductivity. Given that it's concrete, I would expect it to be very low. We would not expect concrete to facilitate a lot of flow. Indeed, it's very low. 3.28 times 10 to the minus 12 feet per second. I will use presets to define the permeability method. The K-min of 1 times 10 to the minus 13 feet per second. I'll hit OK. Great, now we have each of our unsaturated soils defined with volumetric water content data and hydraulic conductivity data. Now for the last soil, I need to define the till, glacial till. And this soil would be a saturated soil, whereas the other soils were unsaturated. That simplifies the parameter process because now I don't need to define the retention curve. Great, so now I have each of the soils defined. I'm going to hit OK. Now I need to have them active in the model. For the dam structure, I will want to use the dam material. So to do that, I will go to the stage settings, and under dam, I will define that as the till material. Then the next would be the sandy clay, then the silt loam, and then finally the concrete. And then I can see that each of the polygons has the soil that I've defined earlier with the color that was attached to the material. Great. So next is defining the boundary conditions. To do that, I'm going to select the line segment section, then highlight each of the regions where a boundary condition needs to be applied. So here I'm going to create an assign new boundary condition. I'm going to give it a total head of 688 feet. And then I'm going to select OK. I'm going to do that for the remainder of the upstream section. I'm also going to do that for the left side of the dam structure. And we can look at the boundary conditions here and see that indeed a constant head boundary is set as 688 total feet of head for each of the 4 lines I've defined. Once that's finished, I need to define the downstream boundary condition. This is going to mobilize the hydraulic gradient necessary for the steady state calculation. To that, I'm going to highlight the line, create and assign a new boundary condition, select total head, and give it 580 feet of head. I'm going to hit OK. Indeed, I can see in real time that it's been applied. And then I'm going to repeat the process for the downstream segment of the model. So indeed, we've generated the upstream and downstream groundwater flow boundary conditions. I can see them summarized here as well in the legend. Next, I need to define zero flux regions. To do that, I'm going to highlight the segment, create a new boundary condition, and I'm going to call it a zero flux section. And then I'm going to repeat the process for every region where I want no flux to occur. This would be at the base of the dam and at the crest of the dam. Indeed, I can see in real time that it's been applied. Finally, I want to generate flux sections. So I'm going to select new. A flux section is defined as a line. So I need the start and end point of the line for the program to generate the flux section. Now I've generated my two flux sections. So I've defined my materials, I've defined my groundwater flow boundary conditions, and I've defined my flux sections. The next step would be to generate the mesh. I need to specify the geometry of the mesh and its coarseness. I will be using triangular elements here. I will hit OK, and then hit generate. Now we can observe the output for our given model. We can see here the variation in pore water pressure. We would expect the pore pressure to be higher on the upstream and then gradually reduce downstream. We can see here also that negative pore pressure is defined in the partially saturated regions. We have negative pore pressure mobilized through the water suction curve we've defined for the materials. We can also view different output settings. So here, instead of pore pressure, I'll put a head, and then I can see the variation in head as a function of the geometry. Okay, thank you for your time, and I hope this presentation was informative.